Hello and welcome back to this MCAT stream. Alright, I'm back, and I could sit here and talk about all of my various excuses for not doing this for a while, but at the end of the day, it's going to be my test score that's tanking because of my own inaction. So, we're back at it again, and let's just jump right back into it. I got to make sure that I cover as much content as possible because goddamn, there's a lot to study. So let's get started. Let's go.
Just like so. And if
All right.
you have
So where we left off,
amino ends
we're gonna be
and the
talking
carboxyl ends line up
about
like so, then this
good old
sheet
protein
is
structure.
called a parallel beta sheet.
We got our secondary and tertiary
And then conversely, if you have
structures
a single polypeptide that is
with
then
the alpha
wrapping up
helices
upon
and the
itself,
beta sheets.
just like this.
I love those two
You
fundamental
have the hydrogen bond
shapes,
stabilizing.
not the building
So-
blocks, the shapes that the building blocks create. Oh, shoot.
Then you have the amino end coming around and lining up with the carboxyl end.
Okay.
And you have a anti-parallel configuration. There is a third level of protein.
All right, so protein structure. Let's see. Where should I place you? Polypeptide, peptide bonds. The main issue with doing this Miro thing is that often I have to find my way around adding more space because a thing that was initially going to be on its own, like peptide bonds, has now been expanded upon. I should have expected that, considering how protein structure is very important. But, silly me, I forgot to do something about that. So, let's go do that right now. Alright, so time bonds. Let's back up a little bit here. Okay. How about we label this as secondary structure? Okay, you know what? I am not going to search up how to do a degree sign. I'm pretty sure there is a hotkey for that, but I am way too lazy, and the point of this is not to make the perfect guide. It's to make a guide for myself to look back and be like, ah, yes, I understand this. And hopefully someone else, because I will, well, I've already been making this publicly, so hopefully if someone finds this and thinks very similarly as I do, well, I hope this helps you. I completely forgot what backbone int
By
was supposed to
backbone.
backbone interactions. Okay. I'm trying to figure out a way to make that smaller, but no. I'm just gonna have to write out the entire interactions because I will not know what int is like 3 days later. Secondary backbone interactions. Alright, so maybe we can form up some wings here. But my alpha helices and alpha helix and beta sheets. And then furthermore, you can get parallel and anti-parallel beta sheets. All right, nice.
Then you have the amino end coming around and lining up with the carboxyl end.
So in that case, what we can say is parallel is N to N. So amino end to amino end, and antiparallel is amino to carboxyl end. All right, perfect. Speed up, shall we?
And you have a anti-parallel configuration. There is a third level of protein structure called tertiary structure, and tertiary structure just refers to a higher order of folding within a polypeptide chain. And so you can kind of think of it as the many different folds within a polypeptide, which then fold upon each other again. And so this depends on distant group interactions, so distant interactions. And just like secondary structure, it is stabilized by hydrogen bonds.
Like a true gamer.
But you also have some other interactions that come into play, such as
long
van der Waals
distance relationships.
You also have hydrophobic packing. And also disulfide bridge formation.
Oh yeah, hydrophobic packing.
So if we explore hydrophobic packing,
me and the boys being scared of water. Me and the boys scared of water.
Found within the watery polar environment of the
Run,
itself.
dude! It's
so if we have water
the water popo.
On the exterior of this
H2Os,
protein,
they're coming.
Then we will find all of the polar groups on the exterior interacting with this water. And then on the interior, you would find the nonpolar or hydrophobic groups hiding from the water. Disulfide bridges, on the other hand, describe an interaction that happens only between cysteines. So cysteines are
very cool.
That have a special thiol group as part of its side chain. And
Love
this thiol
cysteine.
group has a sulfur atom that can become oxidized.
Not cysteine chapel.
And when this oxidation occurs,
amino acid.
You get the formation of a covalent bond between the sulfur groups.
Okay, whoa. Okay, hold up. I'm not even writing down tertiary structure yet. Distant interaction. I mean, now I can make it a lot shorter because I have interactions just below it, so that's perfect. So H bonds. I mean, H bonds are H bonds. You know, they do what they gotta do. Just look at water. Water is pretty cool. And in proteins, they, of course, play a vital role. And so I know hydrophobic clumping and disulfide bonds. What in the world is that little VA? Hold up. I completely missed what she said. Other interactions?
Play, such as van der Waals.
Oh, it's just van der Waals? I mean... Okay, sure. Just for completeness, I'm going to include van der Waals interactions, though. Those are effectively not... they're a given. Alright. Now the important part. Hydrophobic packing. That's the name that the scientists use, not clumping. I personally remember it as such. Okay. You know, every time I try to think of streaming this, I'm always like, oh no, I'm gonna show the world how little I actually remember about my classes. Turns out, I seem to remember a lot, which is good. This is good.
So if we explore hydrophobic packing,
I think I just need to work on my self-confidence.
We have a folded up polypeptide
bridges.
And this protein is found within the watery polar environment of the interior of a cell. So if we have water on the exterior of this protein, then we will find all of the polar groups on the exterior interacting with this water.
Oh my god.
And then on the interior, you would find the nonpolar or hydrophobic groups hiding from the water. Disulfide bridges, on the other hand, describe an interaction that happens only between cysteines. So cysteines are a type of amino acid that have a special thiol group as part of its side chain. And this thiol group has a sulfur atom that can become oxidized. And when this oxidation occurs, you get the formation of a covalent bond between the sulfur group.
Okay, cysteine style oxidizes equals sulfur group bond. Excellent. All right, got it.
The formation of a disulfide bridge happens on the exterior of a cell. And you tend
No
to see
kidding.
the formation of separated thiol groups on the interior of a cell. And that is because the interior of the cell has antioxidants, which generate a reducing environment.
Okay, I did not actually know that. Interesting. So this would be cell exterior. Okay, so exterior cell. Then interior cell is going to have... Uh-oh. I don't have all my tools available on Miro. Where is it? There it is. That's the one I want. So interior. Interior cell has antioxidants which counteract this. So antioxidants. I like how I've never heard about this before, and this is like the first time I've ever had to like think about antioxidants in academic like work. And yet, for some reason, I know what they do, because they are literally called antioxidants. Amazing. Science. If only the rest of science were this good about naming conventions. Oh well.
And since the exterior of a cell lacks these antioxidants, you get an oxidizing environment.
This is more of a
So if I were to ask you which environment
relationship.
favors the formation of disulfide bridges, you would say the extracellular space does.
Yep.
Then there is
Makes
one final
sense.
level of protein structure, and that is called quaternary structure.
Ah, yes,
And quaternary structure describes the bonding between multiple polypeptides. Multiple polypeptides. The same interactions that determine tertiary structure play a role in quaternary structure. And so let's say I have one folded up polypeptide, two folded up polypeptides, and a third and a fourth. The quaternary structure is described by the interactions between these four polypeptides. And within the completed protein structure, each individual polypeptide is termed a subunit. Since this protein has 4 subunits, it is called a tetramer. And so if I were to have 2 subunits, it would be called a dimer, 3 would be called a trimer, and then anything above 4 is called a multimer. So the term for a completely properly folded up protein is called the proper conformation of a protein. And to achieve the proper conformation, you must have the correct primary structure, secondary structure, tertiary structure, and quaternary structure. And if any of these levels of protein structure were to break down, then you start to have misfolding.
Whoa. Many proteins function as monomers and so don't require quaternary structures to be considered properly folded. Yeah, makes sense. Makes sense. All right. So we need multiple polypeptides. Thing I kind of hate about using Miro is that this line is going to show up right through my bubble. That makes me very sad. Oh well. And that I love drawing these mind maps, but by God, they are really hard for me to like ignore the little things. But that's fine. Polypeptides. I'm gonna say... Alright, what is the term that they used for the confirm...
Have 2 subunits, it would be called a dimer, 3 would be called a trimer, and then
Trimer,
anything above
yeah,
4
yeah.
is called a multimer.
Mm-hmm.
So the term for a completely properly folded up protein is called the proper conformation.
Proper conformation. Alright. So this will connect here as well because it can be a monomer, which is totally cool. Monomers are pretty chill. Okay, what I can do is slightly move everything down. Everything. This stuff down a little bit. A little bit. Which will give me space to place some more stuff here. Alright, I want to grab this. I'm going to create a new bubble with the monomer in it. Okay, that is not the right size at all. What the heck? It's literally a dot. Alright, monomer. Alright. I can see how this might be slightly misleading. I think it's not like the polypeptide creates a monomer. It's like the polypeptide is the monomer that will take two paths of either being already properly conformed or needing more help with that dimer, trimer, and tetramer. I think for the most part it makes sense though. Tetramer and multimer. I'm not going to split that up. So let's just keep it as one big bubble. Not super important information.
Of a protein. And to achieve the proper conformation, you must have the correct primary structure,
Just
secondary
keeping
structure, tertiary
completeness
structure,
in
and quaternary
mind.
structure. And if any of these levels of protein structure were to break down, then you start to have misfolding, which can then contribute to any of a number of disease states.
Yep, misfolding bad. Very cool. Unless we want to misfold on purpose, in which case it's good.
Let's
All right.
talk about conformational stability and how this relates to protein folding and denaturation. So first, let's review a couple of terms just to make sure we're all on the same page. And first, we'll start out with the term conformation. And the term conformation just refers to a protein's folded 3D structure, or in other words, the active form of a protein. And next we can review what the term denatured means when you're talking about proteins. And denatured proteins just refer to proteins that have become unfolded or inactive. So all conformational stability is really talking about are the various forces that help to keep a protein folded in the right way. And these various forces are the 4 different levels of protein.
Okay. Proper conformation or conformation stability. Well, I mean, not interchangeable, but conformation stability confirms proper conformation is stable. So I'm just going to put it out here. And then we have active and let's just have denaturation here. Denaturation. Perfect. All right.
Structure, and we can review those briefly right here. So recall that the primary structure of a protein just refers to the actual sequence of amino acids in that protein, and this is determined by a protein's peptide bonds. And then next you have secondary structure, which just refers
Yes,
to
yes,
the
yes. We
local
just covered
substructure
that.
in a protein, and they are determined by backbone interactions held together by hydrogen bonds.
Okay.
Then you have tertiary structure, which just talks about the overall 3D structure of a single protein molecule. And this is described by distant interactions between groups within a single protein. And these interactions are stabilized by van der Waals interactions, hydrophobic packing, and disulfide bonding, in addition to the same hydrogen bonding that helps to determine secondary structure. And then quaternary structure just describes the different interactions between individual protein subunits. So you have the folded up proteins that then come together to assemble the completed overall protein. And the interaction of these different protein subunits are stabilized by the same kinds of bonds that help to determine tertiary structure. So all of these levels of protein structure help to stabilize the folded up active conformation of a protein.
Okay, I'm going to revise our quaternary structure bubble and call it subunit interactions because that makes more sense to me. Well, easier to remember and helps with the clarity. Okay.
denatured protein is inactive. So in addition to the 4 levels of protein structure that I just reviewed, there is also another force that helps to stabilize a protein's conformation, and that force is called the solvation shell. Now, the solvation shell is just a fancy way of describing the layer of solvent that is surrounding a protein. So say I have a protein who has all these exterior residues that are overall positively charged, and picture this protein in the watery environment of the interior of one of our cells. Then the solvation shell is going to be the layer of water right next to this protein molecule. And remember that water is a polar molecule, so you have the electronegative oxygen atom with a predominantly negative charge, leaving a positive charge over next to the hydrogen atoms. The same is true for each of these water molecules. So now, as you can see, the electronegative oxygen atoms are stabilizing all of the positively charged amino acid residues on the exterior of this protein. So as you can see, the conformational stability of a protein depends not only on all of these interactions that contribute to primary, secondary, tertiary, and quaternary structure, but also what sort of environment that protein is in. And all of these interactions are very crucial for keeping a protein folded properly so that it can do its job. Now, what happens when things go wrong? How does a protein become unfolded and thus inactive? Well, remember that this is called denaturation, and this can be done by changing a lot of different parameters within a protein's environment, including changing the temperature, the pH, adding chemical denaturants, or even adding enzymes. So let's start with what happens if you alter the temperature around a protein. And we can use the example of an egg when we put it into a pot of boiling water, because an egg, especially the white part, is full of protein, and this pot of boiling water is representing heat. And remember that heat is really just a form of energy. So when you heat an egg, the proteins gain energy and literally shake apart the bonds between the parts of the amino acid chains, and this causes the proteins to unfold. So increased temperature destroys the secondary, tertiary, and quaternary structure of a protein, but the primary structure is still preserved. So the takeaway point is that when you change the temperature of a protein by heating it up, you destroy all of the different levels of protein structure except for the primary structure. So now let's say you were to take an egg and then add vinegar, which is really just an
Oh my god, it's an entire egg analogy. Amazing. You love to see it. Uh-oh. Nero, what happened? You good?
And if we think about this a little bit more deeply, it kind of makes sense because ionic bonds are dependent upon the interaction of positive and...
Uh-oh. What just happened? Miro just, took away all of my tools. What's up with that? Alright, hang on. Give me 1 second. Still with you. Just need a reload. Hopefully that'll work. If not, I might need to rethink this whole entire stream. Oh well. Come on. Trouble finding the site. Okay. That's not good. I don't like hearing that. Come on. Come on. Oh, oh no. It doesn't help that I'm listening to Ace Combat music. And I just want to fly a plane right now, bro. But I still want to study, so come on, guys. Work with me here. Can get back into the air anytime. I just need to make sure that I'm actually preparing myself for this test. Well, Firefox is not a fan of this. Come on. I am literally trying to pull this up on 2 browsers. Neither of them are working. Okay. Well, maybe I can straight up do it on my phone, but there's no point in streaming then. And we just got started. That's so sad. Session has expired. Okay. That's weird, but alright. Oh. It's loading. Actually loading. I mean, Miro says that it'll have maintenance on September 9th, but I can't help but see that it is the 3rd today, so I don't know why this would be a problem. Maybe it just really needs the maintenance, huh? Well, I did pull it up on my phone. So at the very least, it hasn't imploded on itself. But unfortunately, I don't know if that means that we can stream any longer. Okay. Oh, wait, it's coming back online? Alright. There we go. Come on, you can do it. Okay, we're good. Alright. We're back in it. Okay, wait, what? No, I don't want that shape. Oh dear. I don't like sharp edges except for when I'm using a Windows OS that isn't Windows 11. Cause god damn it, what have they done? Sharpening or dulling out the edges. Come on, guys. We're not Apple. What was I doing? Oh yeah, temp, HP, pH. Playing too many video games. Really? Chemicals? I mean, duh. You're gonna have to be more specific. Chemicals. Amazing. Not like we're doing any chemistry here or anything like that.
Negative charges.
Keep on
so when
going.
you add either an acid or a
Keep
base,
on.
which in the case of an acid is just like adding a bunch of positive charges, you kind of disrupt the balance between all of these interactions between the positive and negative charges within the protein. So now let's look at how chemicals denature proteins. Chemical denaturants often disrupt the hydrogen bonding within a protein. And remember that hydrogen bonds contribute to secondary, tertiary, all the way up to quaternary structure. So all of these levels of protein structure will be disrupted if you add a chemical denaturant. So let's take our same example of a protein with an egg. And say if you were 21 years or older, you got your hands on some alcohol, and you added this to the egg. Then all the
Okay.
hydrogen bonds will be broken up, leaving you with just linear polypeptide chains.
Pour the vodka onto egg.
Hard-boiled egg from the temperature example, and let's eat it. So here's my beautiful drawing of a person representing you eating this hard-boiled egg. Once the egg enters our digestive tract, we have enzymes that break down the already denatured proteins in the egg even further. They take the linear polypeptide chain, whose primary structure is still intact, and they break the bonds between the individual amino acids, the peptide bonds, so that we can absorb these amino acids from our intestines into our bloodstream, and then we can use them as building blocks for our own protein synthesis. And that's how enzymes can alter a protein's primary structure, and thus the protein's overall conformational stability. So what did we learn? Well, we learned that the conformational stability refers to all the
really an example of denaturation.
And this includes all the different levels of protein structure as well as the solvation shell.
Sorry, what?
So what did we learn?
Does disrupt protein? It is not an example of denaturation because denaturation by definition does not disrupt primary structure or alter peptide bonds. Huh. Okay, good point. Good point. Well, wasn't taking that digestion example too seriously. I think I get the point though. Alright. Okay, we actually have a little reading thing here. Wow. It just happens to be talking about planes. Huh. Go figure. Alright. The right structure is needed. Yeah. Okay. So, molecular machines, globular proteins depend finely tuned three-dimensional structures in order to function properly. Linked together. So this is just the written version of everything that we just went over, I think. All 4 levels of protein structure. Interacting with one another in their environment. Okay. Okay, so we're going over some more practical examples. Mentioning CRISPR, I don't think we're going to cover CRISPR just yet. Let's just move on. Enzyme structure and function. Okay, so this is new. Enzyme means substrate. Yes. Enzymes, what they are and what they do. Okay, where does enzyme fit into this? Where can I put that? Where can I put these guys, huh? Hmm. I mean, so far I just kind of put everything on top of this central dogma. I don't think that's necessary. Biological and biochemical foundations. The enzymes, I mean, the fact that there's two different sections dedicated, well, yeah, dedicated to chemistry, but like in slightly different contexts is a little annoying. Because this could fit in either. I feel like enzyme is more fit in the biological section. So let's just create a new thing, and then maybe if I find that it fits somewhere else, we can move that around. So let's start here. All right, enzymes with the substrates and the stuff. Let's go. Definition of catalysis. Okay. Two criteria have to be met. You have to increase the speed, blah, blah, blah. It's not consumed. Yep. Catalyst. Catalyzing. Catalyzing. Right. Alright, so this, it seems like a pretty solid explanation for enzymes through magnets. Like, alright, these two parts are going to stick together if catalysts are there to make sure that they are properly oriented. Yep. And enzymes are biological catalysts, so already I feel pretty solid in placing enzymes here. And I just want to make sure that we remember this is a catalyst. And that is belonging there. I forget the exact name for what N and O would be in this case, though. Are they considered the substrate here? Product of reaction. Yeah. They're both substrates, I believe. Okay. Just had to make sure that I was actually understanding their analogy properly and I didn't just forget anything fundamental. Okay, alright, cool. Enzymes are important. I know that. Energy, burn, this and that. Okay. So, very nice article, but I learned much faster through
So today I want to talk to you about enzymes and how they're critically
videos.
important
Thank you very
pieces of
much.
cellular
Let's go.
machinery. But first, let's review the idea that biochemical reactions happen in the body all the time. Almost every cellular process involves a biochemical reaction at one point or another. You know, the TCA cycle is actually just a series of different biochemical reactions in carbon metabolism. DNA replication, which needs to happen before a cell can go through mitosis, is also just a series of reactions. And this also applies to the expression of genes, going from DNA to RNA to protein. And we need enzymes because enzymes make all of these reactions go much faster. And let's look at this idea a little more deeply and how a reaction will go on differently when it has an enzyme versus not having one at all.
Speed.
So you may be familiar with the reaction where water and carbon dioxide can combine to form carbonic acid. And this is a reversible reaction, so it can go backwards and forwards. Now, when people make soda or any carbonated beverage, they'll start by pumping that soda can full of CO2. And while some of that CO2 will dissolve in water in the can, the soda making companies are able to get a lot more CO2 in the water by using this reaction. You know, the abundant CO2 will react with the water to form some carbonic acid in the can. And when you go to open the can, you'll hear a pop sound, which is really just a bunch of CO2 escaping. But after that, the soda will start to fizz really slowly. And what's happening here is the carbonic acid that was made before is slowly dissociating back to carbon dioxide in water as CO2 escapes. And that extra CO2 that's being made will come out of the soda solution, and you'll see it as little bubbles.
Right, because the equilibrium is shifting.
That person might notice the soda will start fizzing a lot more once it hits his or her tongue. And this is because humans have an enzyme in their blood and saliva called carbonic anhydrase. And this makes the carbonic acid turn into carbon dioxide in water much more quickly. So more CO2 will come out of the can.
Oh, shit.
And this is just one of the many
Didn't know that.
how enzymes make reactions go faster. So how exactly do the enzymes make the reactions go faster, though? Well, they use a bunch of different catalytic strategies to push reactions along a little more quickly. And I'm going to talk about a few of those strategies just to give you an idea of what enzymes are doing. So first I'll mention acid-base catalysis, which happens when enzymes act like either acids or bases. Now remember that acids and bases are proton donors and acceptors. And if you look at this type of reaction, which if you remember from organic chemistry, the keto-enol tautomerization reaction, we have a proton moving from a carbon atom to an oxygen atom. And since acids and bases are pretty good proton carriers, they could both help with this reaction and make it go a little more quickly by helping to move that proton around, instead of this molecule doing it by itself. Our next catalytic strategy is covalent catalysis, which happens when enzymes form covalent bonds with another molecule.
Do I actually want to write? Yeah, let's do that. Plus, they're going to go over it more later, apparently, so... base catalysis... Covalent catalysis, alright. Man, that mentioned OChem though. I kind of miss OChem. Ah. Give me back my puzzles.
Molecule, usually their target molecule. Remember that covalent bonds involve two molecules sharing electrons. And looking at this reaction here, we have a decarboxylation reaction going on, which if you remember from organic chemistry is when a carboxy or CO2 group is being taken off a molecule. And if you remember, these reactions usually have a lot of electrons moving around. So if we had a covalently bound enzyme that could hold on to some electrons and be an electron carrier, or what some people like to call an electron sink, then that would definitely help this type of reaction move a little more quickly. Next we have electrostatic catalysis. Now if you remember, DNA is a very negatively charged polymer because of all the negatively charged phosphate groups that we find in DNA. So if an enzyme had a metal cation on it like magnesium, we could use it to stabilize the negative charge found in DNA and make it a little easier to work with. And DNA polymerase, which is the enzyme that allows DNA replication to occur, does exactly this. And in order for it to help with DNA replication, it needs to find a way to counteract all of the negative charge on DNA, and magnesium ions totally come in handy there. So the last catalytic strategy I want to mention is a little more general, and it has to do with proximity and orientation effects. Remember that in order for two molecules to react with each other, which is usually what enzymes help out with, they need to physically collide at some point. If we have molecule A and molecule B, they'll only react once they crash into each other. And a lot of enzymes are able to bring two molecules close together so that these types of collisions happen more often, making the two molecules react more quickly. Also remember that the orientation of the two colliding molecules in space is also really important. If molecule A and molecule B collide, but one of them is upside down or not in the correct position, then the collision may not result in a successful reaction. So enzymes also make sure that
Alright. And it's also responsible for that little watermill at the end of the, at the end of metabolism. What am I doing again? Oh yes, proximity. And orientation. I can never remember what that molecule's name is, though. Or rather, that protein's name. X. We'll get around to it once we get to the citric acid cycle, so on and so forth.
molecules will collide in the right orientation. And all of this increases the frequency of collision in general, but also helps to make sure that those collisions are successful and result in a reaction. So what did we learn? Well, first we learned that the role enzymes play is to make biochemical reactions happen more quickly. And the next thing we talked about were 4 of the many different catalytic strategies that enzymes can use. We talked about acid-base catalysis, which helps with proton transfer. We talked about covalent catalysis, which helps with electron transfer. We mentioned electrostatic catalysis, which deals with stabilizing charge. And finally, proximity and orientation effects, which increase the frequency of successful collisions between molecules that we want to react.
Okay, hold on. Let me give myself hints as to like what each of these are going to involve so that I can actually remember that. Okay, protons are important there. We got electrons. And then just like sure, like that. Electrostatic. Yeah, I think that's pretty obvious. Okay. I'm earning hella energy points for this. I don't know what you use them
Today we're
for.
going to talk about how
On Khan Academy, though.
influence a reaction's activation energy. But
Yes,
first,
activation
let's review the
energy.
idea that enzymes make biochemical reactions go faster. And in order to do that, they use a bunch of different catalytic strategies. Now, there are lots of different catalytic strategies that enzymes use, but a couple of the key ones are acid-base catalysis, where enzymes use their acidic or basic properties to make reactions go faster by helping out with proton transfer. There's also covalent catalysis, where enzymes covalently bind a reacting molecule to help with the electron transfer. There's electrostatic catalysis, where enzymes use charged molecules or metal ions to stabilize big positive or negative charges. And we also have proximity and orientation effects, where enzymes make collisions between reacting molecules happen a little more often. So what effect do these catalytic strategies actually have on a reaction? Well, let's look at a sample reaction where we're having molecule A being converted to molecule B.
Is there any way to
Now,
get
we
rid of
can process
the
this reaction using
energy
some
points
functions
thing?
forming a
Oh,
diagram.
okay.
And here we'll plot the energy state of our molecules against the progress of the reaction. So essentially, using this graph, we'll follow the energy level of molecule A.
It's
and compare it to
gonna
molecule B.
go a
Remember, the
little
molecule's energy
bit
level is
down
more
because of the
unstable. Something with a
enzyme
lower energy
present
state is
in the
more stable, so it
system.
transforms to a more unstable form that needs an input of energy to get there. So
Right.
looking at this graph, you'll notice that the energy of molecule A will rise up pretty high and then drop all the way down to the energy of molecule B. And we can actually define a couple of values from this graph. The transition state of a reaction, which is represented by this double dagger symbol, is the highest energy point on the path from A to B, and it's where you'll find the most instability throughout the entire reaction. Now, the difference between the energy level where we start and the top of our graph at our transition state is what we call the delta G double dagger, or the free energy of activation. And this is the
Okay. Yeah, I do need to put this down somewhere. Let's see. Just... okay. So, actually, there's a further hierarchy with these four. These are actually the catalysis strategies. So what I want to do is... When does this song play during the game? What? Uh-oh. Oh no, I think I know what it is based on the name. Alright, catalysis structure. Alright, strategies. Catalysis strategies. And boom. Okay. Excellent. Okay, so now I want to talk about activation energy, which will involve the conversation of transition states and free energy of activation. Okay, let me see if I can find that double dagger thing and paste it onto the thing. Called a double dagger so that I can search it up later in case I need it. And then this represents the transition state, which is the state of the react. Wait, what is that? Is that the state of the reactants in the midst of being in the midst of that reaction, or what are we talking about here? Free energy of activation, that makes sense. The amount of energy that is effectively required for the reaction to occur in the first place. That's going to be delta G, dagger. Energy. Okay.
amount of energy that A needs to have in order to break the reaction barrier to ultimately get to point B. You'll also notice that there's a difference in energy between point A and point B, and we call this the standard free energy change for the entire reaction, and it represents the net change in energy levels between our reactant and our product.
Change. Surround. You might notice that I'm not going to be putting all of the various definitions of these things here. Not the point of this exercise. Just trying to make sure that we have all of our thoughts settled and placed in a structure that I can find later if I need to reference it. And so, excuse me, what is happening? Okay, there we go. And we could, yeah. All right. There we go.
And it's also the energy that is released into the environment once the reaction is over. Reactions you typically look at will have their products at a lower energy state than their reactants, since that makes the reaction spontaneous. Now, it's important to recognize that it is the free energy of activation energy value, which is the difference between point A and the transition state, that usually determines how quickly a reaction will go. And usually this energy value is much higher than the free energy change for the reaction, which is why enzymes speed up a reaction by lowering a reaction's activation energy. Now, I want to quickly point out that you may see delta G double dagger written out as EA in some textbooks, and you may see the standard free energy change for the reaction written out as E reaction. And I'm just letting you know, you might see both sets of terms used from time to time. Now, let's look at an analogy to get a closer look at how this all works. And let's say there's a giant hill that you're trying to climb, and it's a pretty steep hill that goes up really high, but you need to get to the other side of the hill. Now, this would be a pretty scary thing on its own, since you would need to go all the way up and then all the way down the mountain to get to the finish line. But if I were to give you a shovel, then now you could dig your way through the mountain and not have to climb up so high. In this example, the shovel represents an enzyme, and the hill represents the activation energy barrier that prevents you from getting to start to finish. By using the shovel, you're able to lower the height of the hill you have to climb. But in both cases, it's important to recognize that you still started and finished at the same points. So let's go back to our example from before with our reaction coordinate diagram. But now, let's say that the reaction has a catalyst. So with the catalyst, the activation energy barrier that molecule A has to overcome in order to get to point B is much smaller. And this will mean that your reaction will have a transition state with a much lower energy, meaning that it's more stable with the enzyme, and also that the reaction as a whole will have a much lower activation energy. Now, it's really important to recognize that, like our example where you're trying to climb the hill, the enzyme will not be changing the starting and ending points of the reaction. It doesn't change molecule A or molecule B. Your starting and ending points are always the same, and the only thing that changes is the path that you take to get from A to B. Now, since our starting and ending points aren't changing, it follows that the enzymes are not used up when they catalyze a reaction, and there is no permanent change to the enzyme following the reaction. So what did we learn? Well, first we learned that enzymes work by lowering the free energy of activation of a reaction, making it much easier for the reactants to transition and form products. And we also learned that the free energy of the reaction doesn't really change when you use an enzyme and when you don't. Second, we learned that despite the changing pathway to get from A to B, the reactants and products do not change when using enzyme versus when not using enzyme. And finally, we learned that enzymes are not consumed when they catalyze a reaction, and the same enzyme can catalyze reactions over and over again.
All right.
So today I'm going to talk to you about the induced fit model.
Oh my god, I keep forgetting that I'm playing this man in 2x speed. Sounds so different.
Catalysis.
All right, there we go.
A lot about how enzymes work. But before we do that, let's review the idea that enzymes make reactions go faster. And when you look at a reaction on a reaction coordinate diagram, you'd see that the catalyzed reaction would have a much smaller activation energy than the uncatalyzed one. Also remember that because of this, the energy
I
of
remember.
reactions transition state
Pepperidge
is
Farm
smaller than the
remembers.
uncatalyzed reactions transition state. So what do enzymes look like? Well, most enzymes are proteins, or at least partially made up of protein. And substrates are any molecule that an enzyme will act on. And often these substrates are the reactants that the enzyme will ultimately help turn into products that are
Oh
reacted.
shoot,
Now,
I still haven't placed substrates on this map here. Okay, let's move activation energy out of the way. That has to do with catalysts. Actually, really, that has more to do with catalysts than it does to do with enzymes being a specific type of catalyst. So, in that case, we're just going to switch over and put substrates here. Okay. And there we go.
Enzymes also have what is called the active site, which is the location on the enzyme where substrates bind, and that's where the reaction ultimately happens. And it's important to recognize that every enzyme has a unique active site that will only bind to certain substrates. And just to clarify, I refer to the active site here as both of the notches found on the enzyme, and not the space in between them. So here, the two substrates I've drawn, the enzyme will only be able to bind to substrate 1, since they fit together like puzzle pieces, whereas the shape of substrate 2 isn't going to fit nicely in the enzyme's active site. Now, since enzymes have unique active sites, we say that enzymes are specific to certain substrates.
Oh, okay. Let me put active site in the middle. Forgot that that would probably come up.
And by extension, so reactions.
Oh.
But let's dive a little deeper into what happens when enzymes and substrates bind each other, and how that
mate.
binding pattern changes as a reaction progresses. So first you have your enzyme here and your substrate over here, and I'm just going to label this with the number 1, since it'll be the first thing that happens in the sequence of events to come. And at this stage, nothing has happened yet, and the enzyme and the substrate have yet to come in contact. So next what will happen is the enzyme will bind to
Got
the
that
substrate,
right.
but this binding won't be perfect. So I'll call this initial binding, which is stage 2 of the process. And what that means is that the forces holding these two together are strong, but they're not at their maximum strength just yet. And enzymes and substrates don't actually fit together quite like puzzle pieces, and they actually work a little bit more like two pieces of clay that will both mold together so that the fit is much tighter. So in our next step, this is exactly what happens. The enzyme and the substrate will both change shape a little bit and bind to each other really strongly. And we call this the induced fit because both the enzyme and the substrate have changed their shape a little bit so that they bind together really tightly. And it's at this point where the reaction that the enzyme is catalyzing is at full force, and this would be stage 3. So our next stage occurs after the reaction is completed, and the binding becomes similar to what it was in stage 2. But the difference here is that there's something different about the substrate. So in this reaction, the enzyme is cutting our substrate into 2 parts, so now the 2 parts have become separated. And this would occur after the reaction is finished, and we'll call this stage 4. Now, in our next and last stage, the products of the reaction have been released from the enzyme, and our enzyme is back in the same state that it was in stage 1, and we'll call this stage 5. Now let's look at this from a slightly different angle. I'm going to label the enzyme as E, substrate as S, and our two products as P1 and P2. And they're going to represent a series of events as different steps in a sequence of reactions. So first we'll have E and S separate, and this is stage 1.
Okay. I don't think initial binding. Well, I guess that probably is a technical term, but I don't believe that that is an important term to remember. The one that I do want to remember is induced fit.
And next, E and S will bind to each other to form an enzyme-substrate complex, which are called ES, and corresponds to stage 2 from before. Now what's really interesting is that in the next step, where we have the induced fit of stage 3, we're actually at the transition state of the entire reaction. And this is the same as that really high energy point that we saw at the beginning of this video, and it's at the point of the transition state where our enzyme is most tightly bound to its substrate. Now I've written the substrate out here with the letter X, because at the reaction's transition state, our substrate isn't quite a reactant, and it isn't quite a product either. It's somewhere in between. So that's why I've written it out as X instead of S. And I've also written this double dagger symbol, which is just a universal symbol for transition states. Now in our next stage, which is after the reaction has occurred, since
Induced fit will include the E-X system plus the dagger.
that exists after the transition state, we have the enzyme bound to the two products P1 and P2, and this was stage 4 from before. And then finally, in our last stage, stage 5, we have our enzyme, which is now separated from our two products P1 and P2. Now, the big takeaway from all this is that binding between enzyme and substrate is strongest at the reaction's transition state, and this is because the enzyme and substrate have molded together, and that's why we call it the induced fit. Now, some enzymes will actually bind to more than one substrate, and if we look at a reaction that might be familiar, which is lactic acid fermentation, we can see that our enzyme, lactate dehydrogenase, will have space to bind two different substrates in this reaction, one space being for NADH and the other being for pyruvate. So enzymes don't necessarily bind just one substrate. Now, sometimes things will bind to enzymes at places other than their active sites, and we call this allosteric binding. So if we have an enzyme here with its active site, a regulating molecule, like an inhibitor, may bind the enzyme at a different location than the enzyme's active site. Now, when something binds to an enzyme like this, it usually has the effect of changing the shape of an enzyme in some way to affect its ability to catalyze reactions. So in this case, when an inhibitor binds the enzyme, it might change the shape of the active site, thereby inhibiting the enzyme as it's no longer able to bind its intended substrate, so they don't quite fit together anymore.
Oh boy. Okay. We got inhibitors in play now, which have always been slightly confusing for whatever reason. I think the main problem with them is that I really struggle to remember what the hell allosteric means. Okay, there we go. But it is quite simple, at least based on this current example. It's got an inhibitor that messes with the shape of the thing, and it's very sad for everyone involved. Except for the inhibitor, who gets to play it off like they did it for fun. Allosteric binding. Okay.
So while enzymes bind reactive groups at their active sites, they can also bind regulators at their allosteric sites, and allosteric sites just refer to any binding site outside of the active site. And remember, allosterically binding molecules can either be activators or inhibitors, any regulating molecule. So what did we learn? Well, first we learned that enzymes are specific, and that they can each bind to only specific substrates to catalyze specific reactions. Next, we learned about the induced fit model, and how enzymes bind their substrates most tightly in the middle of a reaction at the reaction's transition state. And finally, we learned that enzymes have both active sites and allosteric sites, with active sites being where the reaction takes place, and allosteric sites being where regulation takes place.
Okay, nice. 6 types of enzymes. Oh boy. Wait, I might actually learn something here.
About enzymes and all the different kinds of reactions that enzymes can catalyze. But before we do that, let's review the idea that enzymes make biochemical reactions go faster. And if you look at a reaction coordinate diagram, you
Oh my god.
enzymes speed up reactions by lowering their activation energy.
How many times are we gonna repeat this one
So
part,
what an
guys?
enzyme does is someone gives you its
Oh
name.
my
And a great
goodness.
example of this is that one of the enzymes
Alright.
involved in DNA replication is called DNA
Okay,
polymerase,
okay,
which is
okay.
named as such because it acts on DNA and specifically makes polymers of DNA. Now, the suffix ase is usually just one that you find at the end of most enzyme names. Now, another great example is that the enzyme that catalyzes the first step of glycolysis, which you may remember is the reaction between glucose and ATP to form glucose 6-phosphate and ADP, is called hexokinase. And hexo refers to the number 6, which is a reference to glucose being a 6-carbon sugar, and kinase is a term referring to enzymes that add phosphate functional groups to different substrates. So overall, hexokinase adds phosphates to 6-carbon sugars like glucose. Now, generally, every enzyme has a very specific name that gives insight into the specific reaction that enzyme can catalyze. So we can actually divide most enzymes into 6 different categories, based off the kinds of reactions that they catalyze. Now, our first group is the transferase group, and the basic reaction that transferases catalyze are ones where you move some functional
Okay, whoa. Alright, 6 types. Let me create a new thing. Okay. Just to make this a little bit more organized. 6 types here. Transferase, alright.
X from molecule B to molecule A. And a great example of one of these reactions occurs during protein translation, where amino acids bound to tRNA molecules are transferred over to the growing polypeptide chain. So in this case, A refers to our amino acid chain, B refers to our tRNA, and X refers to this lysine residue which is being transferred from B to A. And this reaction in particular is catalyzed by an enzyme called peptidyltransferase, which is an appropriate name since it is a transferase involved in making peptides. Next, we have the ligase group, which catalyzes reactions between two molecules, A and B, that are combined.
Man, I wish my typing speed was a lot higher. Ugh. luckily, there's this whole live game that is a typing speed test, so maybe I can give that a shot. Maybe you can stream it. Who knows? I guess A plus B becomes AB. Okay, this is actually really helpful. I've never figured out, like, I never memorized the different types. Wasn't even aware that they
to form a complex between
were limited to
An example
6.
of a reaction using a ligase that you might be familiar with occurs
Probably
during DNA
not,
replication, when
but
two strands of DNA are being joined together. So in this reaction, A and B represent the two
that's not
separated
how I
DNA
learned it.
polymers, which are being joined to form a single
It is
strand.
what it
And
is.
this reaction in particular is catalyzed by an enzyme called DNA ligase, which is named since the ligase that works on DNA strands. Now, our third group is the oxidoreductase group, which is a little different from the others since it actually includes two different types of reactions. And these reactions involve transferring electrons from either molecule B to molecule A, or from molecule A to molecule B. Now, we say that an oxidase is directly involved in oxidizing or taking electrons away from a molecule, while a reductase is involved in reducing or giving electrons to a molecule. And we call these enzymes oxidoreductases together because they can usually catalyze both the forward and reverse reactions, which is why I've used equilibrium arrows here instead of just a normal single-headed arrow. Now, a great example of an oxidation-reduction reaction occurs during lactic acid fermentation, where electrons are either passed from NADH to pyruvate or from lactic acid to NAD.
This is surprisingly easy to type out, though.
Remember, the word dehydrogenase refers to the removal of a hydride functional group, and that's the same as saying the removal of electrons, since hydrides are basically just hydrogen atoms with two electrons on them instead of just one.
Got the two-way arrow perfectly encapsulated in that equal sign. Very nice.
Typically involved in reactions where a molecule like molecule A is being converted to one of its isomers. And an example of this type of reaction is the conversion of glucose 6-phosphate to fructose 6-phosphate, which is one of the steps of glycolysis that you may remember. Now, this reaction is catalyzed by an enzyme called phosphoglucose isomerase.
Damn, bro, glycolysis is getting hella PR right
Now, our
now.
next category is the hydrolase category. And hydrolases use water to cleave a molecule from molecule A into two other molecules, B and C. And a great example of one of these reactions is the hydrolysis reaction that can occur to peptide bonds. And if we have this lysine-alanine dipeptide here, it can be reacted with water to form two individual amino acids that are no longer bound. And this particular hydrolysis reaction can be catalyzed by a class of enzymes that we call
Tell me there's
serine
6 of
proteases,
these?
some people call serine proteases. And they are named this way because they are
Alright, hold
hydrolases
up.
that use a serine residue as the key catalytic amino acid that is responsible for breaking
Holy moly. Okay, give me a second, my guy. Give me a second. I am very far behind. Hydrolase. Got A plus H2O. O becomes B plus C. Okay. Did not mean to put that period there. Let's fix that real quick. After I move this arrow. Okay. Need to back up. Okay. Pretty good.
peptide bond. Now, our last category is a little more complicated than the others, and it's the lyase group. Now, lyases catalyze the dissociation of a molecule like molecule A
Lyase?
into molecule B and C without using water.
Never heard that one before.
It's an oxidation
Okay.
reaction like an oxidoreductase would. And one example of a reaction catalyzed by a lyase is the cleavage of argininosuccinate into arginine and succinate. And this reaction takes place during the urea cycle, which you also might be familiar with. Now,
write
this
the
specific
projects.
reaction is catalyzed by an
Okay.
enzyme called argininosuccinate lyase, which is appropriately named because it is a lyase that catalyzes the breakdown of an argininosuccinate molecule. Now, it's important to recognize that since lyases don't use water or oxidation to break a bond, they need to generate either a double bond between two atoms or a ring structure in a molecule in order to work. So, what did we learn? Well, first we learned that
Or a
enzymes are
ring
sometimes
structure?
chemical reactions. And next we learned
Or
that six
what?
different oxidation to break a bond. They
Have
need
to form
generate
a
either double
ring
bond between two
structure?
atoms or a ring structure in a molecule in order to work.
Hey? Oh, because I see. Generate either a double bond or a ring structure just because it's not quite as stable without that. Okay. I was like, why are we forming donuts today? What's up with that? Alright. Nice. Requires a little bit more of future investment from the molecule as a whole. Very cool, very cool. I can appreciate an investor. Boom, okay.
Between two atoms or a ring structure in a molecule in order to work. So what did we learn? Well, first we learned that enzymes are sometimes named for their reactions. And next we learned about the 6 different types of enzymes. We have transferases, which transfer functional groups from one molecule to another.
Oh, boy.
Lygases, which ligate or join two molecules together. Oxidoreductases, which move electrons between molecules. Isomerases, which convert a molecule from one isomer to another.
This guy really likes
Hydrolases, which
review.
break bonds using water. And lyases, which break bonds without using water and without
I
using
appreciate it though. Alright. Only love. Okay, let's move this around.
Today we're going to talk about cofactors and coenzymes, and how sometimes they can be essential to proper enzymatic function.
But first, let's review the idea that enzymes make reactions go faster. And they do this by lowering the activation energy peak of their respective reactions. Let's also review
Yes,
the
I
idea that enzymes
know.
bind their substrates at a location on the enzyme called the active site, which is where most of the
Oh
reaction
my
takes place.
god.
Now, not all enzymes are able to catalyze reactions on their own, and some need a little help. So if we have our enzyme here trying to react with our substrate over here, sometimes something called a cofactor or a coenzyme will be needed, which will also need to bind to the enzyme in order for it to function properly. And we're going to go over what coenzymes and cofactors are and exactly how they work. So first we'll talk about what a coenzyme is. Well, coenzymes are organic carrier molecules. And what I mean by organic is that they're primarily carbon-based molecules. And by carrier, I mean that coenzymes hold on to certain things for an enzyme to make the catalysis run a little more smoothly. And a great example of a coenzyme is NADH, which acts as an electron carrier.
Whoa, okay. My map is a mess right now. Hold up. Okay. Enzymes a big topic. Very big. Very important. Alright. You know, maybe... In hindsight, making this... that shape kind of runs into the problem of running into a bunch of other stuff. Uh-oh. Oh well. Coenzymes are organic carriers. Okay, let's put coenzyme on the map. Let's go, gamers. Coenzyme.
And here I've shown NADH dissociating into its oxidized form, NAD+, as well as to a hydride ion, which basically just exists as a pair of electrons that some other molecule would be grabbing. So NAD+ can accept electrons, causing the molecule to be converted to NADH, which could then carry electrons for an enzyme. Now, if you remember the lactic acid fermentation reaction, where pyruvate is converted to lactic acid, you'd see that the enzyme catalyzing this reaction, lactate dehydrogenase, uses NADH as a coenzyme in order to transfer electrons to the pyruvate molecule in order to turn it into lactic acid. And in this sense, NADH is acting.
Okay, so if I look at this map, I'm not going to remember organic carrier. Molecules. Not going to remember that if I don't write it down, so let's do that.
As an electron-carrying coenzyme. Another example of a coenzyme is coenzyme A, which, like NADH, acts as a carrier molecule, but instead of carrying electrons,
that's a very
NADH,
famous one.
Coenzyme A, which we sometimes call CoA, holds on to acyl or acetyl groups instead. And you can see CoA appear quite often in metabolic reactions, where it'll carry these two carbon acetyl groups from one molecule to another. Now, cofactors are a little different from coenzymes. While coenzymes are only really involved in transferring different things from one molecule to another, cofactors are directly involved in the enzyme's catalytic mechanism. They don't strictly carry something like a coenzyme would, but might be stabilizing the enzyme or the substrates, or helping the reaction convert substrates from one form to another. A great example of this is with the enzyme DNA polymerase. Remember that DNA polymerase is responsible for helping out with synthesizing new DNA during DNA replication. Now, you may remember that DNA is a very negatively charged molecule because of all the negatively charged phosphate groups that you'll find around it. Well, DNA polymerase uses a magnesium ion as a cofactor, which can use its big positive charge to stabilize all that negative charge on DNA. And you can see how this is different from a coenzyme, because instead of acting as a carrier molecule, the magnesium ion cofactor is stabilizing the DNA and is more directly involved in the actual catalysis. Now, interestingly, what people normally call vitamins and minerals, like the kinds that a doctor would tell you to make sure you get enough of in your diet, are often different cofactors and coenzymes. And what's special about vitamins and minerals is that your body can't build them up from scratch, and you need to get them from your diet in order to stay healthy. So when we say vitamins, we typically refer to organic cofactors and coenzymes. So two great examples are ones we just discussed. Vitamin B3, which you may see being called niacin on the food label, is actually just a precursor for NAD, and vitamin B5 is just a precursor for coenzyme A. Minerals, on the other hand, are inorganic, meaning they aren't carbon-based, and minerals are usually just cofactors in our body. So magnesium would be a great example of a cofactor that an enzyme like DNA polymerase would use.
Holy sh... What? I've never been that interested in nutrition, so I never like actually looked into what vitamins and minerals are, but that makes so much sense. Of course they're cofactors in enzyme. Okay, that makes sense. My world has been rocked. I am now going to make sure to eat all of my vitamins, or take all my vitamins, or, you know, get all the vitamins that I need, because god damn, okay. Makes sense. Inorganic cofactors. Let's maybe shift everything down a little bit more. Oh my god. Holy crap. What can I say? I'm just too lazy to look into nutrition. And it has bitten me for the past, like, week. Because, man, I've been eating terribly. Just, like, in dieting. On its own, but there's other factors of nutrition that I'm pretty sure to be considered than just the general stuff. What am I doing here? Yes, vitamins. So vitamins are... Science is cool. Science is cool, yo. Science is cool. Mineral. Okay. Excellent.
Now, not all minerals act only as cofactors. Some minerals, like calcium, which can act as a cofactor, is also a critically important component of bone and teeth. And it doesn't strictly act as an enzyme cofactor here, it's actually an important part of the structure itself. So, what did we learn? Well, first we learned that not all enzymes are able to function alone, and some will help. And next,
I learned something today.
Coenzymes, which usually act as carrier molecules, or cofactors, which directly assist with the catalysis the enzyme is doing. And finally, we learned that vitamins and minerals generally refer to dietary cofactors and coenzymes.
Bro. I'm cross my T's and dot my I's from here on out when it comes to vitamins. Oh my god. Alright. My own health aside, let's see what else we got.
So today we're going to talk about the effects of
Local
the environment on
okay.
enzymes, and how a changing environment can affect an enzyme's ability to catalyze a reaction. But first, let's review the idea that enzymes make reactions go faster. And looking at a reaction coordinate diagram, you've noticed that enzymes speed things up by lowering a reaction's
What are we
activation energy.
nervous about
Now, it's important
enzymes
to recognize
DNA
that enzymes
training?
work best in specific environments. And when I say environment, I'm really referring to many different aspects of an enzyme's surroundings, but right now we're really only going to be focusing on pH and temperature values. So let's take another look at this by imagining that we have this person over here, and he's hungry, so he's eating some food. Now, there are a bunch of different digestive enzymes in this guy's body that are going to help him break down all the food he's eating into tiny usable parts. So first, the food will be in his mouth, and one of the enzymes found inside a human's mouth is called alpha amylase, which is responsible for breaking down complex carbohydrates like starches into small, simple carbohydrates like individual sugars.
Okay, so
Alpha amylase is able to work well in your mouth since it functions best at a pH.
y'all think I need to memorize all these different enzymes? I mean, yeah, amylase, yes, okay, so I do know what amylase is. It's just like... Do I need to include this in my map? I don't know.
Moving along, the food that our guy ate is going to go all the way down to the stomach, where a whole different group of enzymes will start breaking down the food. Now, one enzyme that humans have in their stomachs is called pepsin, which breaks down big proteins into smaller peptides. Now, pepsin will be most active at a pH of around 2, which is also the pH of your stomach, which is so low because of all the stomach acid that you find there. Now,
Literally that,
both of these enzymes
like,
work at
meme of
37
Will
degrees,
Smith
which is
and,
the same
like,
body temperature. But you can see
Belair
different enzymes
going
are
like,
functioning at different environmental conditions.
yo!
So what would happen if we took an enzyme and moved it into a different environment?
Whoa!
Well, let's first look at the effects of changing the pH of an enzyme's environment and jump right in with an example. So remember that DNA is a very negatively charged molecule because of all the negatively charged phosphate groups that you'd find on DNA. And in order for the enzyme DNA polymerase to help out with DNA replication, it binds a magnesium ion cofactor, which it uses to stabilize all the negative charge on DNA. Now, under normal pH conditions,
cofactors,
DNA
very
polymerase will
epic.
hold on to that magnesium ion through an electrostatic interaction between magnesium and one of its aspartate residues, which would be deprotonated and thus negatively charged at neutral pH values. Now, if we were to take DNA polymerase and put it into an environment with a reduced pH, then that aspartate residue will become protonated since the pH has dropped so much. In its protonated form, aspartate no longer holds a negative charge and can't hold on to that magnesium ion anymore.
Interesting.
Overall, this means that DNA polymerase won't be able to do its job properly in a low pH environment, and keeping this enzyme at an appropriate pH is essential to its normal function. So now let's take a look at the effects of temperature changes on enzyme function. So remember that proteins need to fold into their secondary, tertiary, and possibly quaternary structures in order to be in their functional form, and significant changes to a protein's temperature can disrupt a protein's folded geometry and cause it to lose its functionality. If we have our same person from before who's really hungry and really wants to eat, but now this person gets sick with a fever, his temperature will rise and a bunch of the digestive enzymes in his body will get all jumbled up and won't be properly folded anymore. And this is why you might have a hard time eating and digesting food.
Okay, hang on. We include pH and then write down that... Proton messes with... reaction. No. Messes with... How do you describe it? Proton messes with... enzyme plan. Yeah. I don't know if that example fully encompasses exactly how that works. I'm just gonna say that the proton is going to mess with whatever is going on. If it's involved, or if there is a charge that is involved that could be messed with a proton being added, then it's gonna be really sad. Temperature change, temp. Okay.
you'll have a fever, and this can sometimes lead you to throwing up anything you'll eat, since all of the digestive enzymes in your body won't work anymore because of the increase in your body's temperature. And the food you eat will just sit there in your body and make you feel sick. So what did we learn? Well, first we learned that enzymes generally function only under very specific environmental conditions, and different enzymes will often function ideally in different environments from other enzymes. And next we learned that changes to an enzyme's environment, like changes to the surrounding pH or temperature, can lead to a loss of enzyme functionality.
All right.
So we're going to talk about enzyme kinetics today. But first,
Or lack
let's
of
review
proton,
the idea
now I
that
think about it.
enzymes speed up reactions by lowering the delta G of the transition state, or lowering the activation energy of a reaction. And also, remember, for this to happen, the reacting substrate, which are called S, will bind to the enzyme E.
That's
to make the
right.
enzyme substrate
That's what it does.
before being turned into product, P. Also remember that enzymes aren't used up when they catalyze reactions, and that's why we have this E at the end of the equation. Now, there's a general method of thinking that we want to use when talking about enzyme kinetics, and that's what I'm going to talk about today. Now, when we think about kinetics, we want to simplify a reaction as a change from A to B. And you may remember that the rate of this change from A to B would be equal to some rate constant K, which is dependent on the environment of the reaction, multiplied by the concentration of our starting material A. So for our sequence that I mentioned before, E plus S going to ES going to E plus P, we'd have two reactions going on, 1 and 2, which would each have their own rate equation. Rate 1 would be equal to rate constant K1 times the two starting material concentrations, which are E and S, while rate 2 would be equal to K2 times the concentration of one starting material, ES. Notice that the reaction 1 has two reactants, E and S, while reaction 2 only has one, which is the ES complex. So what do we mean when we say rate? Well, the rate of a reaction is the speed that the reaction goes at, and we can also call it V, which is a symbol for speed. And for our entire reaction of transitioning S to P, our product, the speed would be equal to the rate of change of our concentration of product with respect to time. Or for those of you who aren't really big fans of calculus, the change in P, delta P, over a change in time, delta T. So to increase the rate that we get in the product, we can do this by either increasing the substrate concentration or by increasing the enzyme concentration.
Okay. I see. All right. So we're talking about rate calculations now. How I'm gonna fit this on there. Let's see. There should be a way to do it. Yeah, I can. Oh shoot, activation energy is so far down there. That's not really necessary in order to figure out how I'm gonna calculate this. I'll just put rate over here then. Rate is equal to V is equal to D, wait, dB over dt okay.
Since we're going to assume that the K value is constant and can't be changed. Now, when we think about enzyme kinetics, we like to assume that we're in a situation where the total concentration of enzyme is constant. And this is generally the case when we're looking at enzymes working in different cells. Now, if we say that we only have 4 enzymes here, and each enzyme can work at a speed of about 10 reactions per second, that would mean that the absolute maximum rate of our reaction would be 40 reactions per second. And this rate we would call Vmax, or max speed. And the idea here is that at really high concentrations of substrate, the enzymes will be saturated and full up with substrate, and won't be able to react any more quickly. And even if we were to really
saturated results in maximum rate, which is equal to Vmax. Makes sense, makes sense.
increase the concentrations of substrate a lot, there will still be a Vmax. There's only so much that we can increase the rate of reaction by increasing the substrate concentration. If we were to look at a graph...
Okay, this is kind of bothering me. What does K mean again in the original rate calculation with the concentration of the reactant?
reaction as a change from A to B. And you may remember that the rate of this change from A to B would be equal to some rate constant K, which is dependent on the environment.
Rate constant. It is dependent on the environment. Okay. In that case, rate constant. Let's see. I can maybe do this then. Nope, not that. Great. Actually, the other thing that I can do here is put that rate equation. Okay. And then show where that k is supposed to go. What that means for this equation. There we go.
So we can increase the rate of reaction by increasing the substrate concentration. If we were to look at a graph and plotted the reaction rate V versus our concentration of substrate, we would see that as our substrate concentration got really, really high, the rate would level off as it approached our Vmax value. So when we think about enzymes and their kinetics this way, we made a couple of assumptions about how our enzymes and substrates are behaving, and I want to talk about these for a moment. The first assumption we've made is that our solutions are behaving ideally, and that we can actually classify our enzymes reaction into two distinct steps. The first being the binding of substrate to enzymes, and the second being the transitions from substrate to product with the enzyme's help. And by assuming that our solutions are behaving ideally, and that we don't have any external factors messing things up, we can simplify our discussion of kinetics quite a bit. Our second assumption is that our two big constants stay constant. We're assuming that our enzyme concentration isn't changing from things like protein synthesis and degradation, and we're also assuming that our rate constant K isn't changing from environmental factors like changes in temperature. Our final assumption is that for our reaction, substrate isn't forming product without the help of enzyme at a big enough rate for us to consider, and that it's negligible. Remember that enzymes only speed up reactions, so while it's possible for the substrate to form product without enzyme, we're going to assume that it's not really happening when we're talking about enzyme kinetics.
Wait, S to P without enzyme is negligible?
From things like protein synthesis and degradation, and we're also assuming that our rate constant K isn't changing from environmental factors like changes in temperature. Our final assumption is that for our reaction, substrate isn't forming product without the help of enzyme at a big enough rate.
Okay, so we're just ignoring the possibility of that occurring without the enzyme. I see. Do I want to include these assumptions? How shall I include them if I want to? Okay, I can do this. I can go here. Assumptions. Of which there are 3. Number 1. Really means that this will be S to ES to E plus P with rate 1, 1. S. Rate 2 is equal to K2 with ES within it. All right. That's a big assumption. That's a big boy. Oh, baby. All right. Constants are constant. Constant. In regards to concentration of enzyme and okay. And SP without enzyme. Without ends. Negligible. Ghibli. Ghibli. Alright. Or Ghibli. I don't know. Neglibi.
Consider that it's negligible. Remember that enzymes only speed up reactions, so while it's possible for the substrate to form product without enzyme, we're going to assume that it's not really happening when we're talking about enzyme kinetics. So what did we learn? Well, first we learned that we can classify enzyme catalysis into two important steps. The first is that the enzymes bind the substrate, and then second, the formation of product. And we talked about how each of these steps has a distinct rate. Second, we learned that if we keep the enzyme concentration constant, then there will be a maximum speed Vmax for that reaction.
Starting to go into my sticky note area. Okay. Maybe we need to move enzymes a little bit further back. Let's get them out of here. All the way over there, my friend. Okay, hold up. Hold up. Where? What is happening? Okay, I did not grab all the things I could have. There we go. Now we can move. Alright. Very nice, very nice. We can keep going. Let's go.
So today we're going to talk about Michaelis-Menten kinetics in a steady state. But first, let's review the idea that enzymes make reactions go faster.
Let's review the idea that enzymes make reactions go faster. Oh boy. Okay, wait. How far are we in this thing? Let's see here. Oh, enzyme kinetics is a like completely different section. Okay. Well, let's keep going then. Finish enzyme kinetics. Then DNA is gonna handle its own section. Gene control, genetics. Okay, we have hella genetics coming up. Evolution and population dynamics. Ooh boy. Oh man. A lot of genetics coming up first before we can get to Krebs cycle. Oh man. We want Krebs cycle to go burr, but we can't do that just yet. Let's keep going with this Michaelis-Menten equation.
Steps. First, the binding event.
First, let me stand up, stretch out a little bit. Actually, I'll be right back. Okay, alright. I'm back. Did you miss me? Anyway.
enzyme to substrate, and
Oh
second,
boy.
to product.
Reactions go
And each of these
faster. Oh
reactions
my
has its own rate.
god.
Let's also review the idea that if we keep the concentration of enzyme constant, then at really high substrate concentrations will hit the maximum speed for a reaction, which we call Vmax. So first, we'll talk about the steady state assumption and what that means. So like I said before, there are two steps to an enzyme's catalysis. Now, when we use the term steady state, what we mean is that we're at a point where the concentration of ES, or enzyme substrate complex, is constant, which means that the formation of ES is equal to the loss or dissociation of ES. Now, notice that I used equilibrium arrows between these steps, and that was to show the idea that these reactions, like any reaction, can go forwards or backwards. Our enzyme substrate complex doesn't have to form products. It could just as easily dissociate back to an enzyme and a substrate molecule. So I'll call these reverse reactions -1 and -2. If we look at that in terms of our rates, we can say that the rate of formation of ES would be the sum of rate 1 and rate -2, since both of these reactions lead to ES. And the rate of loss of ES is equal to the sum of rates -1 and 2, since both of these lead away from ES. Now also remember
Makes sense. Okay. Formation of ES. Yeah. Steady state assumption. Okay. Can I include that in my assumptions? I mean, it is an assumption that is related to rate, so I'll go ahead and include it. Maybe in a different spot, though. Hell, we can do this and go rogue all on our own. Fly off the handle with the steady state. Assumption. Oh my god. Face the Soldier is playing. Da, 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 da. Da, da. Probably one of my favorite moments in gaming. That little drop in that song there. Really feeling like a hero. Da, 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 da. Man, I can't micromanage this stupid little S thing. Ah, whatever. Alright. It's all good. Let's just keep going. Steady state assumption. ES is constant.
go back to reactants, since these reactions are usually thermodynamically stable. So rate -2 is going to be so small in comparison to rate 1 that we can really just cross it out, which means that we can swap out that second double-headed arrow for a single-headed arrow. So using this information, let's do some math. Now I'm going to be deriving a new equation. This can get a bit confusing, so don't worry if you have a little trouble with this. Just rewind the video a couple more times if you need to. So I'll start out by drawing the same sequence I did before, with the 3 different reactions, and also write out that steady state equation I mentioned before, where we have rates forming ES equal to rates taking away ES. Now the first thing I'll do is swap out those rate values where the rate constants times the reactants for those reactions. So rate 1 will be equal to K1 times E times S, and so on for the other two. Next, I'll introduce a new idea and say that the total amount of enzyme available, which we'll call ET or E total, is equal to the free enzyme E plus the enzyme bound to substrate, or ES. And using this equation, I'm going to rewrite the E on the left side of our equation as the total E minus the ES, which would be equal to the E we had before. On the right side of the equation, I just factored out the common term ES.
Okay.
Next, I'm just going to expand the left side of the equation, so take a moment to look at that. And now what I'm going to do is I'm going to divide both sides of the equation by K1. So K1 will disappear on our left side, and on our right side, I put K1 in with all the other rate constants. Now, since all these rate constants are constant values, I'm going to combine them in this expression of K minus 1 plus K2 over K1 into a new term, Km, which I'm going to talk a little bit more about later. So in this next line, I've done two things. First, I've thrown in that Km value that I just mentioned, but I've also added ES times S to both sides of the equations, and thus moved it.
Okay, whoa. Hold up. Let me see here. Maybe I can... Ugh. See, these mind maps are mainly for vocabulary terms, but once you get into the mathematics, it's like... not really sure how to demonstrate a proof or calculation in this format. At the very least, Km is a distinct thing that we can point out is equal to a K minus 1 plus K2 all over K1. That I can show, at least.
From the left side to the right. In the next line, I've done two things. First, I switched the left sides and right sides of the equation.
The main issue is, will I be able to remember what K minus 1 and K2 is?
So I can move that term to the right side.
I guess
So
we'll
I'll make
see.
a number here, and now what I'm going to do is remind you that the speed of our whole process, which I'll call VO, is equal to the rate of formation of our product, which we called rate 2 before, which is also equal to K2 times ES. So now using our equation over here, I'm going to multiply both sides of the equation by K2. Now here's where it gets really tricky. Remember that if we're at our max speed, so a reaction speed VO is equal to Vmax, which happens when our substrate concentration is really high, then our total enzyme concentration is going to be equal to ES, since all of our enzyme is saturated by substrate, and there won't be any free enzyme left. So K2 times ET instead of times ES would be equal to Vmax instead of being equal to VO, like you see at the top. So I'll make some room here and then sub in K2 ES for VO and K2 E total for Vmax, and then we finally get to our end equation, which is called the Michaelis-Menten equation, and is super important when we talk about enzyme kinetics. So let's take a few steps back.
Okay. All right. So I can just put the Michaelis-Menten equation on its own. Let's just put it over here, or we can put it down here. Michaelis-Menten. It is very famous and very important. Vmax over Km. Menten. That's a big M, isn't it? But a little K. Oh, okay. Km plus this. There we go. Now I can have this big boy here. And change this to a little K, big M. Excellent. Let's go.
Kinetics. So let's take a few steps back and talk about the Michaelis constant. So first, I'll write out the Michaelis-Menten equation, and if you remember, we created this new term which I called Km, but we never really talked about what it meant, so let's get to that. Now, if you bear with me for a moment and pretend that Km is equal to our substrate concentration, then we can sub in that value into our Michaelis-Menten equation, which would put 2s on the bottom, the sum of s plus s, and the s cancels out, and we'll be left with Vmax over 2. And what this means is that Km, which we call the Michaelis constant, is defined as the concentration of substrate at which our reaction speed is half of the Vmax. So when VO is equal to 1/2 of Vmax. And if you look at that on a graph from before, you'd see that Km is a substrate concentration specific to our circumstances, where our rate is at half of its max. And the lower our Km, the better our enzyme is at working when substrate concentrations are small. And we can use this Km term to quantify an enzyme's ability to catalyze reactions, which we call catalytic efficiency. So I'll rewrite the Michaelis-Menten equation.
Whoa, okay. Hold up. Alright, so Michaelis constant. That's the first definition that they gave us. The Km is equal to that stuff. It's not the technical definition though. Technical definition is where is substrate concentration, where VO equal to 1/2 Vmax. Alright, excellent.
Km, the better our enzyme is at working when substrate concentrations are small. And we can use this Km term to quantify an enzyme's ability to catalyze reactions, which we call catalytic efficiency. So I'll rewrite the Michaelis-Menten equation. Remember, we defined Km as a substrate concentration, where VO is 1/2 Vmax. And since it's a concentration, it will be in units of molar, or moles per liter. But now I'm going to throw a new term at you called Kcat, which is equal to the maximum speed of a reaction divided by the total enzyme available. And we call this the enzyme's turnover number. And all this term is how many substrates an enzyme can turn into product in 1 second at its maximum speed. And we measure it in units of seconds to the -1, or per second, as in reactions per second.
Km. Okay. Measured in moles. Okay. And then I want to include the Kcat, which is the turnover number. Kcat. Vmax. Okay, I need to watch out for big T. I need to put a little t. Hopefully I can tell what that is. Turnover rate. Calculated in inverse seconds.
So we can define an enzyme's catalytic efficiency as a combination of Km and Kcat, and we do this by saying it's equal to Kcat over Km. So a higher Kcat or a lower Km would result in an increase in an enzyme's catalytic efficiency. And every different enzyme has a different catalytic efficiency in certain conditions, and we can use this term to score enzymes on how good they are.
Huh. Interesting. Catalytic fancy. That's the KCAT divided by KM. Right. Good, good, good. Nice. Looking good, looking good. Like where this is going.
Enzyme has a different catalytic efficiency in certain conditions, and we can use this term to score enzymes on how good they are. So we covered a lot of content in this video, but the really crucial points to remember are first, the idea of the steady state assumption that we make when looking at enzyme kinetics, and this is where we assume that the ES concentration is constant, meaning that the formation and loss of ES are equal. Second, we derived the critically important Michaelis-Menten equation, which you should consider committing to memory. And third, we talked about how you can score how good an enzyme is at speeding up reactions by looking at that enzyme's catalytic efficiency, which is a combination of two new terms we learned about, KCAT and KN.
All right, cooperativity. Let's go, let's go.
So we're going to talk about cooperative binding, which is a very interesting topic when discussing enzyme kinetics. But first, let's review the idea that we can divide enzyme catalysis into two steps. First, the binding of substrate.
Oh shit, he actually changed it. Oh my god.
Which is very useful for quantitatively looking at.
But let's review that you can split it into two. Excellent. All right.
Now, the first thing that
That's
I want to talk about is that some
refreshing.
enzymes can bind more than one substrate, and not all enzymes have just one active site. So E plus S can form ES through what I call reaction 1, but some enzymes can react with another molecule substrate to form ES2 through what I call reaction 2, and again to form ES3 through reaction 3, and so on.
Oh
Now,
boy.
these enzymes can form product at any stage of this process, no matter how many molecules of substrate are bound. Now, you would expect the rate of reaction 1 to be faster than the rate of reaction 2.
Yeah,
But
that's
looking at
how
the example of
you
three substrate binding sites, there are 3 empty sites available for substrate
use a
1 for reaction 1, and only
ribosome.
2 available for reaction 2, so you would expect rate 1 to be faster. Similarly, rate 2 would be faster than rate 3 for the same reason, and the idea is that the active site saturation does not increase with substrate concentration linearly. Now, I get that can be a mouthful, so let's look at it graphically, but we're also going to show an exception to this rule. So in this first graph, I've plotted substrate concentration against the percent saturation of the enzyme, and as you can see, the curve levels off as substrate binding sites become occupied. It becomes difficult to bind more substrate molecules as you have more substrate molecules bound.
That makes
Next, I want to
sense.
draw a different curve that you also might see in some enzymes, and that's where substrate binding happens more quickly as binding sites become occupied. Substrate binding changes substrate affinity, and we call this cooperativity. Now, with respect to cooperativity, we can find 3 new ideas.
Okay. Where are we gonna go with this? Okay, first of all, I want Michaelis-Menten to be up here, along with what is related to it, so that's good. Let's go find substrate. There it is. Bring out substrate. Point it to cooperativity. Excellent. Okay, and substrate binding changes substrate affinity. So that's kind of the definition that we're given here. Okay, I know that I said that I wasn't going to put down definitions. I'm totally putting down definitions. Mostly because, like, you can have vocab terms stand on their own without definitions if they're surrounded by other vocab terms that make that relationship obvious. Cooperativity is just kind of on its own right now.
And we call this cooperativity. Now, with respect to cooperativity, we can find 3 new ideas. Positively cooperative binding occurs when substrate binding increases the enzyme's affinity for a subsequent substrate. Negatively cooperative binding occurs when substrate binding decreases the enzyme's affinity for subsequent substrate. More than you would normally expect, and non-cooperative binding is the same as the first example, where substrate binding does not affect the enzyme's affinity for substrate molecules. So let's look at this graphically. If we have a protein with, let's say, 5 binding sites, and plot the fraction occupied versus the substrate concentration, we would come up with 3 possible curves. The green curve, which takes on a sigmoidal shape, would represent an enzyme.
Okay, whoa, whoa, whoa.
Substrate molecules.
All right. Positively cooperative binding. Substrate binding increases the affinity. Okay, so this is the case where I don't actually need to write this down. Or I don't actually need to write the definitions. I just need to write down the names. Because that is self-explanatory, which is great. Love it when something's self-explanatory. Okay, positive cooperative binding. Negatively. Non-cooperative. Ding.
So let's look at this graphically. If we have a protein with, let's say, 5 binding sites, and plot the fraction occupied versus the substrate concentration, we would come up with 3 possible curves. The green curve, which takes on a sigmoidal shape, would represent an enzyme with positive cooperativity. The blue curve, with a hyperbolic shape, would represent an enzyme with non-cooperative binding. And the red curve would represent an enzyme with negatively cooperative binding. Now remember that the effects of cooperativity are only seen after some substrate has already bound, which is why the difference in the fraction occupied between the 3 curves is much smaller at smaller values, like the 1/5 that I've shown here, than it is at the higher values. So let's look at a specific example of a couple proteins. So hemoglobin, or HB, is the oxygen-carrying molecule that you find in human blood, and it can bind up to a total of 4 oxygen molecules, and it exhibits positively cooperative binding. Myoglobin, on the other hand, which is the oxygen-carrying molecule that you find in muscle tissue, can only bind 1 oxygen molecule in total. And since it can only bind 1, it must exhibit non-cooperative binding, since there's no subsequent substrate to speak of. Now, if we make a graph where we plot the fraction of active sites bound in each of these proteins versus the pressure of oxygen, remember oxygen is our substrate here, and since it's a gas, we're going to use pressure instead of concentration, you can see that the red sigmoidal curve associated with hemoglobin's positive cooperative binding looks different from the blue hyperbolic curve associated with myoglobin's non-cooperative binding. So what did we learn? Well, first we learned that some proteins can bind more than one equivalent of substrate. And next, we learned that there are 3 different types of cooperativity: positive, negative, and non-cooperative. Finally, we learned about proteins that exhibit 2 different types of cooperativity, which are the oxygen-binding molecules hemoglobin and myoglobin.
All right. Steric regulation.
So today we're going to
Excellent.
talk about how allosteric regulation can affect enzyme kinetics. But first, let's review the idea that an enzyme's catalysis can be divided into 2 steps. First, the binding of enzymes to substrate, and second, the formation of products. And using this information, we can derive the Michaelis-Menten equation, which allows us to look at an enzyme's rate of product formation with respect to substrate concentration. Also remember that substrates will typically bind to enzymes at the active site. So what do we mean when we say allosteric regulation? Well, we know that enzymes usually have an active site where substrates can bind, but enzymes can also have what we call an allosteric site. And these allosteric sites are places on the enzyme where any enzyme regulator can bind. And I put this star here just to point out that allosteric sites can be anywhere on an enzyme, and there can be any number of them as well. So what do we mean when we say regulators? Well, we generally say that there are 2 types of regulators. There are allosteric activators, which increase enzymatic activity and activate them, and allosteric inhibitors, which decrease enzymatic activity and inhibit the enzymes. So let's take a look at what we mean by increasing and decreasing enzymatic activity from a kinetic perspective. So remember the Michaelis-Menten equation, and if we're assuming substrate concentration to be constant, then there are 2 ways to influence enzymatic activity, or VO. And in this first graph, I've drawn 3 different curves, and the blue curve represents the enzyme functioning without an allosteric regulator at all. The red curve represents an enzyme with an allosteric inhibitor, and the green curve represents the enzyme with an allosteric activator. And in this example, the activators and inhibitors affect VO through either increasing or decreasing Km, since the Vmax values seem to be pretty close between the 3 curves. So an activator here might be decreasing Km. Now in this next example, we have the same 3 colored curves, but instead of Km changing significantly, the regulators seem to be changing Vmax, with the activator increasing the Vmax value. So now that we've talked about activators and inhibitors, let's introduce the idea of the feedback loop. And the basic idea is that a feedback loop is when you have downstream products regulating upstream reactions. And I understand this can be a mouthful, so let me show you this little reaction sequence where we have A forming B through reaction 1, and B forming C through reaction 2, and so on and so on. Now let's say that molecule F acted as an activator for the enzyme powering reaction 1. So it had a positive effect on enzyme 1's activity. Now we would call this a positive feedback loop since molecule F increases the rate of reaction 1, which then causes even more F to be made, so we increase the rate of formation of molecule F. Now let's say molecule F had a negative effect on enzyme 1, we would call this a negative feedback loop since molecule F decreases the rate of reaction 1, which leads to a decrease in the rate of formation of molecule F. So let's look at an example of a feedback loop, just to really drive home the point if you're still confused. Now, phosphofructokinase is an enzyme involved in glycolysis, and it catalyzes the conversion of fructose 6-phosphate and ATP to form fructose 1,6-bisphosphate and ADP. Now remember that glycolysis is a metabolic process that cells use to generate ATP. So here our molecule F, or downstream regulator from the last example, is ATP. And it turns out that ATP is an allosteric inhibitor of phosphofructokinase. And this makes sense because if ATP is at a high level, then it's like the cell saying, we have ATP, and we don't really need anymore. And we don't need phosphofructokinase to push glycolysis along. So this would be a good example of a negative feedback loop, since making ATP slows down glycolysis and thus slows down the rate of ATP production.
Right.
Now, because ATP is both an allosteric regulator and a substrate for phosphofructokinase, we can call it a homotropic inhibitor, which is a new term, and we call it a homotropic inhibitor because the substrate and the regulator are the same molecule. Now, AMP, which is used up ATP, is an activator for phosphofructokinase, and this also makes sense because
Okay. I'm starting to. All right. Let's see. The reason why I went silent there is because I'm trying to figure out exactly how to write this. Feedback loop. So, what I can put is a. Okay. Here's what we're gonna do. We're gonna have allosteric regulation. Separate box from feedback loop. Which then, not ironically, fittingly, we'll loop back around to include allosteric inhibitors and activators. So let's put this here. Loop this back around. Can't see. There it is. Okay. Boom. Okay, amazing. That's done. Okay, so homotrophic and heterotrophic are both terms concerned with feedback loops. They're specifically referring to the cause of the loop being a molecule inhibiting itself or activating something else. So homotrophic with heterotrophic. Okay.
Now, the final point I want to make is that specific reactions make excellent control points for long multi-step processes. And remember that glycolysis is a 10-step sequence. So why is there so much regulation going on for this one step? Well, this reaction in particular has a very negative delta G, and it's actually negative 4.5 kcal per mole. And that means that it's not easily reversed, since there will be a big release of energy from the reaction. And this makes this
very
step
spontaneous
excellent
towards
control point
the
for all together,
right
since it's more or less
side.
a one-way reaction. So what did we learn?
Right.
Well, first we learned about the concept of allostery and how regulatory molecules can bind to allosteric sites instead of active sites. Second, we learned that these allosteric regulators influence an enzyme's kinetics by increasing or decreasing Km or Vmax. And third, we learned about what a feedback loop is and how in long multi-step processes like glycolysis, the best control points are highly committing steps, the ones with very negative delta G values.
Wait, very
In long multi-step processes like glycolysis, the best control points are highly committing steps, the ones with very negative.
control points. Oh, Stonehenge defensive. That was Cape Rainy for a second there. All right. And it's done. Non-enzymatic protein function. Let's go.
Okay, so we're going to be talking about non-enzymatic protein function. And before we get into what exactly that means, let's just say we are playing a game of categories, and the next category that comes up is protein, and you have to list all the different types of protein that you know. And so you're like, oh, I totally got this. We got beef and pork and chicken, right? Those are different types of protein, and that's true. But what about the biochemistry type of protein? As in,
What about the
large biomolecules
biochemistry
that are made
type
up
of
amino
protein?
acids. What are all the different types of proteins?
Oh my god.
Then. And so that's a little bit tougher. And so that's the point of what we're going to be talking about today, is to talk about all the different types of proteins and the different
my god, we're
functions
talking about
that they perform.
if we're talking about
And
food protein,
so
that makes me hungry.
The key to understanding
Oh, Lord.
proteins as we go forward is understanding one unique characteristic about proteins. And that unique characteristic is that they can bind various biomolecules, and they bind specifically and tightly. And so just keep that concept in mind as we're talking about all the different functions of proteins, and that'll help you understand how they are able to perform the vast array of functions that they do.
Okay.
So I like to think of proteins as being in one of two main classes. There are the enzymatic proteins, so enzymes, and then the non-enzymatic proteins, or we'll just call them the non-enzymes. And so let's back up just a minute. What exactly are enzymes? What do they do? Enzymes are, in a nutshell, little chemical reaction machines. They can catalyze all sorts of
We
chemical
literally
reactions,
just
so
went
they
over
catalyze
that.
reactions
Oh
that
my
help sustain
goodness.
life. And so they're really the
I just need to
workhorses
remind
of
you
helping
that
build things as needed.
enzymes
And by adding
make
enzymes can
reactions go
accelerate
faster.
the rate and specificity of these chemical reactions. And one good example example of this that you're probably familiar
Real
with already
quick.
is DNA polymerase, which catalyzes the synthesis of new strands of DNA.
Ooh,
And
baby.
probably even more familiar to you are the enzymes in your saliva.
Yeah,
so
yeah,
every time you
yeah.
eat, there's one enzyme in particular called amylase,
Non-enzymatic.
which is responsible for breaking down starch into sugars. So amylase is another example of a protein that has enzymatic function. And just notice for a second that both of these enzymes end in ASE. And so, in general, if you see a protein and it has this sort of ending, you should be thinking to yourself, oh, I bet this is an enzyme, an enzymatic protein. So that's a good rule of thumb. Now, non-enzymatic proteins or non-enzymes are all those proteins that carry out functions that require the capacity to bind, but not necessarily to catalyze a reaction. And so what are some examples that we'll be talking about of non-enzymatic protein function? Well, there are proteins that function as receptors or ion channels in a cell membrane, and we'll talk more about that. And then there are proteins that are transport proteins. There are also motor proteins, and then a special class of proteins that function as an integral part of the immune system, and those are called antibodies. And so we'll go through each of these examples of non-enzymatic protein function one by one. So
Great.
let's give ourselves a little bit more room to talk about those. Now, let me quickly
Antibodies are pretty cool.
Not all proteins are always either an enzyme or a non-enzyme. Oftentimes, they have characteristics of both. And so just keep that in mind as I'm going through and highlighting the non-enzymatic properties in this video. Okay, so starting with receptors and ion channels. There are certain proteins that exist in the membrane of a cell and function as either receptors or ion channels. Now, receptors are proteins that receive or bind a signaling molecule. So let's draw a cell here. We're going to draw the membrane bilayer here. And so here would be my exterior of the cell, and here's the interior of the cell. And within this membrane bilayer, you can find a receptor protein. So we'll draw that here. And this receptor protein will bind a signaling molecule, also known as a ligand, which then induces some sort of chemical response in the cell. So one example of a receptor protein and ligand pair is an insulin receptor and insulin. So let's say this ligand is insulin, and this is the insulin receptor. Now, insulin is a hormone that's released by the pancreas in response to an increase in blood glucose levels. So let's say there's extra glucose because you just ate a piece of pizza or something. So let's say there's an increase in glucose around, and then insulin is going to be released by the pancreas in response to this increase in blood glucose. And then once it's released, it binds to its corresponding receptor on certain cells, which leads to a cascade of signals within that cell. And this allows it to then absorb this excess glucose into the cell. And then likewise, you can also have an ion channel that also spans the membrane bilayer. So let's extend this lipid membrane bilayer, and then we'll draw in an ion channel protein here. And so likewise, this protein spans the entire bilayer of the cell, and it acts as a pore or a channel through which certain ions, say calcium, can enter or exit the cell. So it can come in and come out through the same channel. Okay, so next up are the transport proteins. And now these proteins are responsible for binding small molecules and transporting them to other locations in a multicellular organism like humans. And the
Pretty straightforward stuff.
high affinity for
Just
the ligand
covering
and high concentration.
the brand
So at high
overview of
concentration a ligand, you
various
have high affinity of the protein for that ligand, and at low concentration, you have low.
non-enzymatic proteins. So we're just kind
And
of
a good example of
chilling.
this is hemoglobin. So hemoglobin is present in red blood cells, and it picks up oxygen in the lungs. So here are my lungs, it's high in oxygen in your lungs, and then delivers this oxygen to tissues. And we'll draw tissue here, say it's muscle tissue, where it's present in low concentrations. And so this is a great example of a transport protein at work.
Yeah.
So next up are the motor proteins,
Classic.
which include myosin, kinesin, and dynein.
Oh, motor proteins are fun, though.
These proteins are really
I
crucial
love
for cellular
myosin
functioning,
and kinesin.
Myosin specifically is a protein responsible for
and
generating
dynein.
force exerted by contracting muscles.
I believe.
every time
I
you flex
think
your
they
bicep like
all have the little, like, walking structure. Definitely dynein, where like, let's just walk along this like skeleton within the cell and just like woo, 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 woo. Transport or motor proteins transporting all that shit around
Your
while
myosin protein
walking.
in your muscles are contracting and generating that force.
So cute.
Now, kinesin and dynein are motor proteins that are responsible for intracellular transport. And then dynein in particular also plays a role in the motility
Yeah,
of the cell.
my-
These
okay.
little extensions of a cell.
I
projectile.
was like
And
a little
kinesin
confused
is
with
the-
myosin there, but yeah, myosin is just your muscles. But kinesin and dynein, they're the ones that walk a little bit. Oh boy. Motor proteins, including myosin, kinesin, and dynein. I think I can go ahead and include kinesin and dynein in their own little bubble. They deserve to be together. There we go. Yay for them. All right. There are your motor proteins. Very nice.
protein can lead to a rare disease called primary ciliary dyskinesia. So in primary ciliary dyskinesia, you can see there's some sort of dyskinesia or problem in movement for the cilia. And mutations in a particular dynein protein lead to this rare disease in which the action of the cilia of the cells lining the respiratory tract fail to function. And this leads to a decrease in mucus clearance from the lungs. and therefore an increased susceptibility to chronic infections like pneumonia and bronchitis. So as you can see, these motor proteins are really important. And then finally, our last class of non-enzymatic proteins that we'll be talking about are the antibodies of the immune system. Now, antibodies are protein components of the adaptive immune system whose main function is to bind foreign antigens and target them for destruction. So in this case, the antigen, which comes from any foreign substance, say a virus or something like that, is the antibody's ligand. So here's an example of an antibody, and then here's the antigen. And the antigen is really just the antibody's particular ligand. So you can think of antibodies as being like little red flags for the body's immune system, letting us know that, hey, this thing is not supposed to be here, we need to get rid of it somehow. And it's important to know that an antibody's affinity for its target antigen is extraordinarily high. So the affinity is strong, really high. And so there you have it. You can see all the different types of non-enzymatic roles or functions that proteins can play, either as receptors or ion channels, as transport proteins, motor proteins, and then highly specific antibodies in our immune system.
This is green. Okay. Right? Covalent modifications. Hang on. I want to double check. How far are we in this? I think that's the last one in this section. Excellent. All right. Good.
So today we're going to learn about covalent modifications to enzymes. But first, let's review the idea that enzymes make reactions go faster. And looking at a reaction coordinate diagram, you'd
He's
notice
back.
that enzymes do this by the reaction's activation.
Ah!
Also,
Not
before we talk about
again.
modified enzymes, I want to remind you that
I
not all
swear
enzymes are proteins. And
to
often when we think of enzymes, we think of proteins, which are amino acid molecules,
Klaus, bruh. Oh shit! No, 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 that's not what I meant to do. Oh no! No, 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 no! I messed it up. Whatever. Come on, take me back. There we go.
quaternary structures. But there are also many different kinds of enzymes that aren't proteins. Inorganic metals like magnesium or small organic molecules like flavin can also act as enzymes. But for the purposes of this discussion, we're going to focus on the proteins. And to be clear, when we say covalent modifications, we refer to modifications to a protein that involve forming or breaking covalent bonds. Now there are tons of different covalent modifications that we can observe, so I'm only going to touch on a select few to get the point across. And the first category of covalent modifications I want to talk about are small post-translational modifications. Now when I say translation, I'm referring to the process of translation where amino acid polymers are synthesized. And when I say post-translation, I refer to events that take place after that initial synthesis. Now when I say small, all I'm referring to are modifications that involve small functional groups being added or removed from an enzyme. And again, there are many different types of these, but I'm just going to touch on three. So methylation is a modification of a protein that involves the addition of a methyl group, or CH3, to a protein. Acetylation involves the addition of a cell group, and glycosylation involves the addition of a sugar molecule. And these are just three examples of a huge list. And these modifications, although small, can have pretty significant impacts on the protein as a whole. And to discuss this, I want to mention the example of acetylation of a lysine residue on a protein. So as you may know, lysine is an amino acid that has an extra amino group on its side chain that can act as a base and carry positive charge. If we were to acetylate this lysine residue and add an acetyl group to the amino nitrogen, which is a covalent modification, the electron withdrawing effect of the acetyl group would prevent that nitrogen from carrying positive charge and modify the behavior of that amino acid. The loss of that positive charge can change a few properties of the amino acid, including changes to the lysine's acidity and basicity, since it can no longer exchange protons as well, and it will also influence lysine's electrostatic interactions with other charged molecules, since it's lost that positive charge. So even a small modification, like the addition of a cell group, can have significant impacts on the protein overall. Moving on, I want to discuss another way in which covalent modifications of enzymes is relevant, and that's in reference to zymogens. Now, a zymogen is an inactive form of an enzyme that requires a covalent modification in order to become active. And a big example of these zymogens in biology are the digestive enzymes that the pancreas releases so that you can digest food. One of the enzymes that the pancreas releases is called a trypsinogen, which is a zymogen, as indicated by the protease.
Acetylation.
Now, this is an inactive form of a protease enzyme that is shipped to the intestine, and once in the intestine, it's covalently modified by an enzyme called enterokinase, which converts it to its active form.
Inactives enzyme that require covalent. Okay. I mean, I know that that is an example. I just want to... Or I know that spotlight lysine acetylation is an example. I want to include that. Cyanogens are the ones that should be included for sure, though. There we go.
Trypsin. Now, this is to prevent trypsin from breaking down proteins that we need in the pancreas, since it's inactive at that point, as trypsinogen, and only allows it to break proteins down in the intestine after it's encountered enterokinase. Notice how you can distinguish zymogens from their active form by their name, in that zymogens have ogen added to the end of them. Now, the last example of covalently modified enzymes that I want to discuss is the subject of suicide inhibition. Now, when we think of enzymatic inhibition, we usually think of competitive, non-competitive, and uncompetitive inhibitors, which follow certain patterns in terms of their effects on enzyme
Suicide
resistance. But there's another type of inhibitor that's a little different. This is the
inhibition.
suicide inhibitor. Suicide
What?
inhibitors covalently bind the enzyme and prevent it from catalyzing reactions. And what's interesting is that since these inhibitors form covalent linkages to the proteins, they rarely unbind, which is why we call them suicide inhibitors, since after they bind, that's it for them. And this is what distinguishes this type of inhibitor from the other three that you might be familiar with. So what have you learned?
Yeah.
Well, we talked about three very different things today that all have to do with covalent modifications to enzymes. First, we talked about small post-translational modifications like methylation, acetylation, and glycosylation. Second, we discussed zymogens, inactive proteins that require covalent modification to become active. And finally, we talked about suicide inhibitors, which are enzyme inhibitors that permanently bind their target.
That's wild. They couldn't have called them permanent inhibitors. I'm just saying. All right, interesting. All right then. Well, that covers enzymes, and I think that's it for today. Oh, I'm gonna have to pretty this up, aren't I? Oh boy. I'll see y'all probably tomorrow, actually. because I'm going to make this a very regular thing. And hopefully we'll get through this entire thing quite quickly. Post-haste, because, boy howdy, we gotta get moving. And get practicing, for real. So, see y'all then. Continue to study. I don't know. I still need to figure out a sign-off thing for this. And the MCAT, the cat, the